In this session, we are going to see gate questions on the topic oscillator. We all have studied about oscillator. It is an electronic circuit that produces sinusoidal signals at the output side by taking only DC power supply. Right? First, let us start from the gate 2004 question. The value of C required for a sinusoidal oscillation of frequency 1 kilohertz in the circuit of the figure is, so an oscillator circuit is given to us and its frequency of oscillation is given as 1 kilohertz. We need to identify the value of capacitor. Okay, so first let us try to identify what oscillator is this. Once if we identify the oscillator, we can obtain the expression for frequency of oscillation. From that, we can calculate the value of capacitor. Right? The given circuit, if you consider, is it inverting amplifier or non-inverting amplifier? Because the inverting terminal is provided with negative feedback and the other end is connected to ground potential. Right? And the actual input signal appears only at the non-inverting input. When we compare with the four oscillators we have discussed, like Wien bridge oscillator, phase shift oscillator, and other LC oscillators, normally the phase shift oscillator and two LC oscillators operate in non-inverting mode. Inverting mode. Amplifier introduces 180-degree phase shift. Okay. So here in the feedback network from the output, we are connecting a capacitor and resistor in series. Here we are connecting capacitor and resistor in parallel, right? So RC series network, RC parallel network. Output of this parallel network becomes the input for the amplifier, right? So this oscillator comes under RC oscillator category. Why? Because the feedback network involves only two components, resistor and capacitor. So under this RC, we have two categories. One is Wien bridge oscillator, another one is phase shift oscillator. Okay. In case of Wien bridge oscillator, we use this series parallel arrangement of RC component that act as notch filter, right, or frequency selection network. Only one particular frequency of signal will be allowed to the input of the amplifier. Okay. And according to our discussion, we know the formula for frequency of oscillation. What is the formula for Wien bridge oscillator? F equals 1 by 2 pi RC, isn't it? F equals 1 by 2 pi RC is the frequency of oscillation for Wien bridge oscillator. In this, frequency is given as 1 kilohertz. So 1 into 10 power 3, 1 kilohertz. And we need to know the value of R and C. Okay, what is the value of C given? C, it is not given in the question. We need to identify the value of C because the value of C is required. Whereas the value of R is given in the question, its value is 1 kilo ohm. So substitute here R equals 1 kilo ohm. What will happen when the R becomes 1 kilo ohm in this equation? If you substitute, we are interested to find the value of C, right? So C comes to the other side. We can write it as our C, capacitor C equals 1 divided by 2 pi times F into R, because the F comes to the denominator, its value is 1 into 10 power 3. So 1 times 10 power 3. In addition to that, if you see, resistor also 1 kilo ohm. Frequency is 1 kilohertz. Resistance also 1 kilo ohm means, so 1 into 10 power 3, right? So I simply write it as 10 power 3. What are the options given to us for the formula? 1 by 2 pi times microfarad. Because 10 power 3 into 10 power 3, 10 power 6. When it goes to the numerator, 10 power 3 and 10 power 3 becomes 10 power 6, and numerator means it becomes 10 power minus 6. This is nothing but micro. So 1 by 2 pi times microfarad. What about the other options? If you consider it is 2 pi times microfarad. No, 2 pi is in the denominator, right? So this cannot be the answer. Again, if you look at the next one, 1 by 2 pi times root 6, right? This root 6 formula appears for RC phase shift oscillator. Here we are not dealing with RC phase shift oscillator. It is Wien bridge oscillator. A simple way to differentiate between Wien bridge and RC phase shift oscillator is RC phase shift oscillator is operated in inverting mode. The signal, feedback signal will be connected to inverting input. Whereas in case of Wien bridge oscillator, the feedback signal is connected to non-inverting amplifier. So there is no phase shift by the amplifier stage. This formula is applicable for Wien bridge oscillator. I'm sorry. This is for RC phase shift oscillator. So this cannot be applied here. The same here also 2 pi times root 6 means they have brought this to the numerator side. Still it is not applicable. So the answer is 1 by 2 pi microfarad. Okay. So here is the answer. Now from GATE 2003, from the topic oscillator. Now if you look at here, an amplifier is represented by a triangle, right? And there are some feedback elements. Output of this is given to some RC circuits. Here 3 RC circuits are connected, having capacitor in series, resistor in parallel, right? These 3 RC networks, output will be given as input for the amplifier again. Okay, the 3 RC sections together form the feedback network that is used for frequency selection, right? That decides the particular frequency at which the amplification should take place. Okay, and here it is given that oscillator circuit shown in figure has an ideal inverting amplifier. Sir, ideal inverting amplifier means here it is inverting amplifier. So whatever the input you apply, output will have 180-degree phase shift. And its frequency of oscillation in terms of hertz they ask. Normally, if you consider in the feedback network, we have only R and C component means it is called RC oscillator. Under RC oscillators, we have 2 types. One is Wien bridge oscillator, another one is phase shift oscillator. Here we are using inverting amplifier means it introduces phase shift. Because of this, it is called phase shift oscillator. Here amplifier introduces 180-degree phase shift. Your feedback network also introduces another 180-degree means the total phase shift around the loop is 360-degree or 0-degree. Okay, this 360-degree or 0-degree indicates that whatever the input signal we apply, it has experienced 180-degree phase shift by the amplifier, another 180-degree phase shift by the feedback network means once again when it comes to the input, it will be in phase with the input signal so that it appears as positive feedback. So in order to get positive feedback, you should have the condition that the total phase shift around the loop must be 360-degree or 0-degree. Okay, students? Right. So here is the question given to us. Oscillator circuit is given. It is ideal inverting amplifier. Its frequency of oscillation they have asked. It is basically phase shift oscillator. What is the formula for frequency of oscillation? For phase shift oscillator, F equals 1 by 2 pi RC times root 6, right? There is a big length of derivation that we can achieve through simplifying this RC network one by one. And finally, we obtain the expression for beta, where beta is nothing but output of the amplifier is the input for the feedback network beta, right? And this is the input to the amplifier, which is nothing but output to the output of the feedback network. So beta is nothing but VA divided by the output of the amplifier, which is nothing but input to the feedback network. Okay, VA by V naught is nothing but beta. After simplifying this, you will get an expression In that expression, we have to consider imaginary part, make it 0. After simplification, you will obtain the expression as 1 by 2 pi RC times root 6. Right? Now let us check the options here. 1 by 2 pi root 6 times RC. Here 1 by 2 pi RC. This is the expression for Wien bridge oscillator. And 1 by root 6 times of RC, it is actually 2 pi is missing. This is the expression for angular frequency. This is normal frequency F. When it is angular frequency, this formula may be correct. They have asked its frequency of oscillation in terms of hertz. If it is angular frequency, its unit is radians per second. Right? If they ask the expression in terms of radians per second, means we can take this option. Because it is in hertz, we have to go for this expression only. The last one, it is given 1 by root 6 times 2 pi c. R is missing here. Okay, so this is not applicable. This is for angular frequency for RC phase shift oscillator. This is the normal frequency 1 by 2 pi RC times root 6. And this expression is applicable for Wien bridge oscillator 1 by 2 pi RC. Okay. Now we look at the gate question from the year 1990. Figure shows an RC phase shift oscillator. So in the question itself given that it is RC phase shift oscillator where your BJT along with some set of R and C components create the amplifier and the RC section here, right? This forms the feedback network. 3 RC sections form the feedback network. So this is your RC oscillator. In the feedback, we have 3 RC sections and the amplifier in CE mode introduces 180-degree phase shift. Here the RC section introduces 180-degree phase shift. So the total phase shift around the loop will be 360-degree. Okay. Solve the network to find the minimum value of HFE. HFE is nothing but a H parameter. It is for forward current gain. H suffix F represents forward current gain and this E denotes under common emitter configuration. So forward current gain in common emitter configuration. This is something like beta of the transistor only, which is the ratio between output current and the input current. Current gain means output current by input current. Here output terminal is your collector. Input terminal is nothing but your base. Emitter is common for input as well as output. So output current divided by input current is nothing but your beta, and that is also denoted as HFE. Right? And next, minimum value of HFE for the transistor for oscillations to be possible. Okay. Also determine the frequency of such oscillation. So there are 2 things we need to find. One is HFE, the minimum value of HFE we need to find out, and also the frequency of oscillation we need to find out. Take C equals 0.01 microfarad and HIE equals 2 kilo ohms. HIE means input impedance under common emitter configuration for the transistor. Okay, this is for the input impedance of the transistor. If you replace the transistor by its H parameter model, its input impedance will be 2 kilo ohms. Is this clear? So these are the parameters given. From this, we need to find out HFE and frequency of oscillation. Sir, there are straightaway formulas are available. If you can substitute, you can solve this problem. First one, for frequency of oscillation, when we use BJT network, the frequency of oscillation of RC phase shift oscillator is 1 by 2 pi RC times root of 4K plus 6. Okay, in case of op-amp based oscillator, this 4K term will be neglected because here the amplifier is based on BJT. This term comes into picture. What is this K? K is nothing but the ratio between the collector resistance RC and the resistance used in the feedback network called R. What is the value of RC here, collector resistance? Its value is 1 kilo ohm. The resistance used in the feedback network R also 1 kilo ohm. So here, according to this condition, the value of K is nothing but 1. So if I substitute in this, it becomes 4 times 1, 4, 4 plus 1, 6. So here it becomes root of 10. 1 by 2 pi RC times root of 10. This general formula is for RC phase shift oscillator when it is constructed with the help of BJT based amplifier. Right. What about HFE minimum? The minimum value of HFE of the transistor is required in order to establish oscillation. It is 4K plus 23 plus 29 by K. Okay, this is again a formula which requires derivation available in standard textbooks. You can refer to it. 4K plus 23 plus 29 divided by K. Here the value of K equals 1. If you substitute here, what will happen? 4 times 1, 4 plus 23 plus 29 divided by 1. So it becomes 29. Adding the 3, you will get 29 plus 23, 52, 52 plus 4, 56. The minimum value of HFE is 56. And here if you substitute like 2 pi RC, it is given, the value of R is 1 kilo ohm. And the value of C is given in the question itself, 0.01 microfarad. If you substitute, here it is root 10, you will get the frequency of oscillation. Before I conclude, I would like to clarify one important point here. Here you can notice that in this RC section we have R 1 kilo ohm. Here it is R 1 kilo ohm. But here the value of R is given as 4 kilo ohm. Then in this formula, should I take 1 kilo ohm or 4 kilo ohm means this resistance is selected by considering various resistance of the amplifier also. That is why it is replaced by 4 kilo ohms. Okay. Sir, why sir? How it has come into this value as 4K? If you draw the DC equivalent for this particular biasing arrangement, this 4 kilo ohm will come in parallel to this. This is clear. For DC conditions, this DC power supply will be connected to ground potential, and this 4K other end is connected to ground potential, means here also it is connected to ground potential. So this K, one end connected here to base, the other end connected to ground. Here also one end connected to, for this 4K also one end connected to base, the other end connected to ground potential, means these two will come in parallel. So 4K in parallel with 4K. What is the equivalent value here? From the biasing arrangement itself, it gives you the value of 2 kilo ohms as the total resistance. Again, one more factor is there. In the question itself, it is mentioned that the input resistance of the amplifier HIE is given to be 2 kilo ohms. So when you replace the transistor by its equivalent model, it has its input resistance of 2K. And from the biasing arrangement, we have the resistance of 2K, which comes in parallel with this. So this 2K resistance in parallel with the 2K resistance will give you overall equivalent resistance of 1 kilo ohm. Okay, so this is the reason why I am considering this as 4 kilo ohms. So basically it is 1K, 1K, 1K. The overall input resistance experienced at this node is only 1 kilo ohm. So when you bring this 4K in parallel to this, and after that you have to bring the 2 kilo ohm input resistance in parallel to this, the overall resistance experienced here is only 1 kilo ohm. Is this clear? So in this way we obtain the expression for frequency of oscillation and HFE minimum. Match the following. The question is slightly different. So they have given 3 oscillators, namely Hartley oscillator, Wien bridge oscillator, and crystal oscillator. We have to match with another group stating that something may be low frequency oscillator, high frequency oscillator, stable frequency oscillator, relaxation oscillator, and a negative resistance oscillator. How can I identify this? First, let us try to classify each of these oscillators in group 1. Then it is easy for us to solve this one. Hartley oscillator is basically a type of LC oscillator, whereas Wien bridge oscillator is a type of RC oscillator. Your crystal oscillator, the third category of oscillator, which is used to produce fixed frequency oscillation, right? We don't have any design parameter with the crystal oscillator. It is only the size, mechanical size of the crystal which decides the frequency of oscillation. So at the time of manufacturing itself, they shape the crystal to bring a required amount of frequency of oscillation. So from design point of view, we have nothing to do with this, right? So only fixed frequency oscillation it produces. Whereas Hartley oscillator and Wien bridge oscillator, we have the options to change the value of either LC or RC so that we can vary the frequency. This LC oscillator normally is suitable for radio frequency oscillation, very high frequency oscillations. Whereas RC oscillators are suitable for audio frequency oscillations, right? So with this idea, let us just check the answers one by one. Low frequency oscillation. Low frequency means audio frequency oscillation. So among the three, Wien bridge oscillator is the low frequency oscillator. High frequency oscillator. Here we have two options. It may be either Hartley oscillator or crystal oscillator. But if you consider the next options, other options, stable frequency of oscillation, if you consider, when compared to RC and LC oscillators, the quality factor of crystal oscillator is very high and it produces stable frequency of oscillation. Okay, because of this reason, the stable frequency oscillator is considered to be your crystal oscillator. So high frequency oscillator is given with the choice of Hartley oscillator. Sir, we have two more options, right? One is relaxation oscillator. The other one is negative resistance oscillator. Relaxation oscillator is normally constructed by UJT, uni-junction transistor. By connecting some capacitor at its gate terminal, we have to charge and discharge the capacitor. Based on that, it produces some output. This is called a relaxation oscillator. This is constructed by using UJT. And negative resistance oscillator means a special kind of diode called tunnel diode. This tunnel diode exhibits the behavior called negative resistance. So using tunnel diode in the oscillator circuits is possible, and it also produces a signal that's called a negative resistance oscillator. So tunnel diode based oscillator is negative resistance oscillator. UJT based oscillator is called a relaxation oscillator. These options are not given in the question. Option A matches to 2 in the group. Hartley oscillator is high frequency oscillator, and option B, Wien bridge oscillator, matches with option 1 in group 1, that is low frequency oscillator, and crystal oscillator matches with the stable frequency oscillator. Okay,